Scientists spent decades telling the world that Pluto was a cold, dead, geologically boring rock on the frozen edge of the solar system. They were wrong about almost everything. When NASA's New Horizons spacecraft finally reached Pluto on July 14, 2015, after traveling more than 3 billion miles over 9.5 years, the images that came back did not show the crater, scarred, frozen wasteland that every model and every prediction had described. They showed something that should not have been possible, something that sent planetary scientists scrambling to rewrite textbooks, something that has since led to one of the most extraordinary hypotheses in the history of planetary science. If you are not yet subscribed to this channel, do it before this video ends, because what NASA got wrong about Pluto and what New Horizons actually found out there changes how we think about where life in the solar system might exist. And that is a conversation worth following closely. Let us start with the mission itself, because understanding what it took to get there makes what was discovered even more remarkable. New Horizons launched in January 2006 aboard one of the most powerful rockets available at the time. The spacecraft was accelerated to a speed exceeding 36,000 miles per hour, making it the fastest human-made object ever launched from Earth at that point. To give that speed context, the Apollo astronauts needed 3 days to reach the moon. New Horizons passed the moon's orbit in less than 9 hours. The entire solar system was effectively flashing past its instruments at a speed that compressed distance into time in a way that is genuinely difficult to conceptualize. And yet, even at that velocity, the journey to Pluto took 9.5 years. For most of that time, the spacecraft was in electronic hibernation. Engineers powered down most of its systems to conserve energy and extend the hardware's operational life. Once a year, they sent a wake-up command, checked the spacecraft's health, confirmed it was still on course, and put it back to sleep. 9 years of silence in the absolute emptiness of interplanetary space, coasting through darkness toward a destination that had never been visited by anything from Earth. The mission had a structural limitation that created enormous pressure as the arrival date approached. New Horizons had no braking system capable of slowing it into Pluto's orbit. The dwarf planet, as gravity is too weak to capture a spacecraft moving at that speed without a major propulsion burn that the spacecraft was not designed to execute. This was a flyby mission, meaning there would be one pass, one window, one chance to gather everything that 9.5 years of travel had made possible. Scientists compared it to standing on the roof of a high-speed train and trying to photograph a fighter jet coming the other way. One blink, and the opportunity is gone forever. The additional complication was the communication delay. By the time New Horizons reached Pluto, it was so far from Earth that any radio signal traveling at the speed of light took 4.5 hours to make the one-way trip. There could be no real-time control, no adjustments based on what the cameras were seeing, no live guidance from mission controllers. The spacecraft had to execute hundreds of pre-programmed commands entirely on its own, pointing cameras, activating spectrometers, measuring the atmosphere, and recording everything while simultaneously navigating through a region that might contain rings of dust and debris that could destroy it. After completing all of that, it had to survive long enough to turn its antenna toward Earth and transmit the signal confirming it was still intact. Scientists describe the hours of waiting after the closest approach as the longest of their professional lives. If anything, the size of a grain of rice had struck New Horizons at that relative velocity, it would have been vaporized instantly, and the images it had taken would have been lost forever. When the signal finally came through and the mission controllers confirmed the spacecraft was alive and transmitting, the reaction in the control room was not professional restraint. It was pure relief and genuine celebration, because everyone in that room understood exactly how narrowly the alternative had been avoided. Then the first image appeared on the screens, and the mission transformed from a triumph of engineering into a scientific revolution. The world that planetary scientists had confidently described for decades as a cold, all cratered, geologically dead remnant from the early solar system was nothing of the kind. What New Horizons revealed was a world of stunning complexity, geological activity, and physical variety that defied every prediction that had been made about it. The most immediately striking feature was what scientists named Tombaugh Regio, a broad, bright, roughly heart-shaped region covering an area approximately equal to the combined size of Texas and California. This region appeared almost completely free of impact craters. In planetary science, the absence of craters on a surface is one of the most reliable indicators of geological youth. Every solid surface in the solar system accumulates craters over time as meteorites and small bodies impact it. Surfaces that have been unchanged for billions of years are heavily cratered. Surfaces that have been recently reshaped by geological processes are smooth because those processes have erased the older impact record. Tombaugh. Regio's near-complete absence of craters meant its surface was young in geological terms, possibly only millions of years old rather than billions, suggesting that something was actively renewing it. Close examination of the imagery revealed what that something was. The smooth, icy plain was not a uniform surface. It was broken into a pattern of roughly polygonal shapes, individual cells, ranging from 12 to 18 miles across, the surface expression of an active convection process happening beneath it. Warm material from depth was rising, cooling at the surface, and sinking back down, creating a slow, churning motion that continuously brought fresh material to the surface and erased the older record. The best terrestrial analogy scientists could find was a lava lamp, though the material involved was not liquid rock, but exotic ice. Pluto's heart was not frozen solid, it was flowing. This discovery immediately raised a question that should not have had an easy answer. How could Pluto, a body this small and this far from the Sun, have any internal heat source at all? Objects of Pluto's size lose their primordial heat of formation within a relatively short window of geological time. By any conventional calculation, Pluto should have been a frozen solid from the core outward for most of its history. Where was the energy coming from that was driving active geological convection billions of years after formation? The answer involves a combination of factors that together produce an outcome nobody anticipated. The interior of Pluto contains radioactive elements within its rocky core, the same decay processes that contribute to Earth's internal heat. Uranium, thorium, and potassium isotopes decay over geological timescales, releasing heat in the process. In a small body, this contribution is modest, but it is not zero, and over geological time, it accumulates into a meaningful energy budget. Additionally, the chemistry of whatever material exists inside Pluto contributes to keeping it from freezing solid. The internal ocean, whose existence the mission data strongly implied, appears to contain large concentrations of ammonia dissolved in water. Ammonia is a powerful antifreeze. Its presence dramatically lowers the freezing point of water, allowing liquid to persist at temperatures that would otherwise solidify a pure water ocean completely. The evidence for a liquid subsurface ocean was not limited to the convective surface pattern. The surface of Pluto shows extensive fracturing, long cracked systems running across the landscape that are consistent with what happens when a freezing process is expanding from the inside. The physics is exactly analogous to what happens when you put a sealed water bottle in a freezer. The water expands as it freezes, and if the container cannot accommodate that expansion, it cracks. Pluto's surface is cracking in a pattern consistent with a subsurface layer of water that has been gradually freezing at its outer boundary over billions of years, expanding as it does so and forcing the overlying crust to accommodate that expansion through fracturing. This fracture pattern became, as researchers described it, an ironclad alibi for the subsurface ocean. Nothing else in current planetary science produces that specific surface signature on that scale. The mountain ranges that New Horizons revealed added another layer of astonishment. Pluto's Tenzing Montes and Hillary Montes, named after the first climbers to summit Everest, rise to heights between 1 and 2.5 miles above the surrounding terrain. These are not mountains made of rock. They are mountains made of water ice, which at Pluto's surface, temperature of around negative 230 degrees Celsius, behaves mechanically like rock because it is far below any temperature at which it can deform plastically. Water ice at that temperature is structurally rigid, load-bearing material. These mountain ranges are as geologically credible as the Rocky Mountains, built from a material that we normally experience as fluid, but that becomes stone-hard under Pluto conditions. And the snow on those mountains is not water. At Pluto's temperatures and atmospheric conditions, methane can condense and deposit on elevated terrain just as water vapor condenses as snow on Earth's mountain peaks. New Horizons found bright deposits of methane frost on the peaks of Pluto's mountain ranges, creating a visual landscape that looked eerily familiar while being chemically utterly alien. The imagery of mountains with bright, snowy peaks rising above darker lowlands activated every human association with alpine scenery, while describing conditions that no earthly life could survive for a second. The cryovolcanoes were among the most dramatic individual features revealed by New Horizons. Wright Mons, one of the largest identified examples, has a base diameter of approximately 90 miles and rises 2.5 miles above the surrounding terrain. It is taller than Japan's Mount Fuji and covers a surface area comparable to the state of Connecticut. Instead of erupting molten rock as volcanic features on Earth and other rocky bodies do, Wright Mons and similar structures on Pluto are thought to erupt a mixture of water and ammonia in a slushy, semi-liquid form. The existence of these structures confirms active geological processing connecting the interior to the surface, providing a physical pathway through which material from the subsurface ocean can reach the exterior. The atmospheric discovery added yet another dimension to Pluto's complexity that contradicted the expectation of a simple, frozen world with at most a thin frost of surface ice. Pluto has an atmosphere, thin by Earth standards, but present and dynamic. The famous image from New Horizons, showing the limb of Pluto backlit by the sun, revealed a layered blue haze extending well above the surface. a nitrogen-dominated atmospheric structure with photochemical hazes at multiple altitude levels. The blue color of the haze comes from the same basic physics that makes Earth's sky blue, the scattering of shorter wavelength light by small particles in the atmosphere. This atmosphere is not stable in the way Earth's atmosphere is stable. Pluto follows an extremely elongated elliptical orbit that takes it significantly closer to and farther from the Sun over its roughly 248-year orbital period. When Pluto is closer to the Sun, surface ices warm and sublime into gas, expanding the atmosphere. When Pluto is farther away, those gases freeze back out of the atmosphere onto the surface as a global frost. The atmosphere literally collapses periodically, the sky's gaseous component dropping as snow onto the landscape, and then rebuilds again over decades as the orbit brings the planet closer to solar radiation. No other world in the solar system has been documented to have an atmosphere that completely disappears and reforms on an orbital timescale. The Tartarus Dorsa region revealed yet another landscape that had no precedent in planetary exploration. Across this area, methane ice has been sculpted by sublimation processes over millions of years into tall, narrow blades rising as high as the Empire State Building, packed closely together in fields extending across vast areas. Moving through this, terrain would be physically impossible for any human explorer. The blades are too closely spaced and too sharp-edged to navigate, creating a landscape that looks like a natural version of an impenetrable barrier field extending to the horizon in every direction. The dark reddish equatorial regions that New Horizons imaged, given the designation Cthulhu Regio by the naming team, represent a different kind of surface chemistry. The reddish coloration comes from complex organic molecules called tholins, produced when ultraviolet radiation from the Sun breaks down simple molecules like methane and nitrogen in Pluto's atmosphere. These molecules then polymerize into larger, more complex organic compounds that settle onto the surface and accumulate as the reddish coating that gives the equatorial regions their distinctive appearance. Pluto's surface contains organic chemistry that, while not biological in origin, involves the kinds of carbon-containing molecular building blocks that are precursors to biochemistry under more favorable conditions. The dunes spotted near the edge of Tombok Regio represented another completely unexpected finding. Pluto's atmosphere is extraordinarily thin, roughly 100,000 times thinner than Earth's at sea level. The expectation was that such a thin atmospheric environment would be incapable of moving surface material, but the dunes are there, their morphology clearly indicating that some form of wind transport has been actively moving particles across the landscape. The mechanism appears to involve nitrogen gas subliming from the surface ice and creating localized gas flows strong enough to transport fine grains of methane ice across the landscape, building dune structures in a process that has no direct terrestrial equivalent. All of these discoveries individually would have been remarkable. Together, they form a picture of Pluto that is not just different from expectations, but fundamentally more interesting. The hypothesis that has emerged from the combined analysis is that Pluto may harbor conditions in its subsurface ocean that are not entirely hostile to simple life, drawing a comparison to the hydrothermal vent ecosystems on Earth's ocean floor that support rich biological communities entirely independent of sunlight. Organic material from the surface falls through fractures in the crust, enriching the subsurface liquid environment. Radioactive decay provides heat from below. The chemical environment is extreme by terrestrial standards, but not categorically different from environments on Earth, where life has established itself. The discovery in 2019 of spectral signatures indicating fresh ammonia near surface fractures provided a further data point in this picture. Ancient ammonia cannot persist at Pluto's surface because ultraviolet radiation breaks it down relatively quickly on geological timescales. Fresh ammonia at fracture sites implies that material from the interior, where ammonia is shielded from surface radiation, has recently been brought to the surface through the fractures. Pluto exhaled while New Horizons was watching. The internal ocean is communicating with the surface in real time through the fracture system. What New Horizons achieved was not simply adding one more data point to our inventory of the solar system. It transformed our understanding of where complex geology, chemistry, and potentially biology can exist in conditions that our prior models would have ruled out entirely. The lesson of Pluto is that the universe is consistently more creative than human models predict, and the assumptions we make about what is possible in extreme environments are consistently revised toward more possibility rather than less as we gather better data. Drop your thoughts in the comments about which discovery from New Horizons surprised you most. And subscribe before you leave, because the next video on this channel covers the current science on what the subsurface ocean environments of Pluto, Europa, Enceladus, and Titan have in common, and what that tells us about the broader question of where in the solar system we should be looking most seriously. The dwarf planet that everyone ignored turned out to have more going on beneath its surface than almost anything else we have visited. To fully appreciate why the scientific community was so comprehensively wrong about Pluto before the flyby, it helps to understand the specific reasoning that led to the pre-mission consensus and why that reasoning seemed so solid at the time. Pluto was discovered in 1930 by Clyde Tombaugh at the Lowell Observatory in Arizona. For the following 85 years, it was known only as a point of light in telescopes, a speck that moved slowly against the background stars in a way that revealed its orbital period and allowed rough estimates of its distance and size. Early estimates of Pluto's size were wildly wrong in the large direction. Initial calculations suggested it might be comparable in size to Earth. As measurement techniques improved over the following decades, those estimates shrank steadily. But by the 1970s, it was clear Pluto was small. By the 1990s, telescope observations had refined the estimate to a diameter of roughly 1,400 miles, making it smaller than Earth's moon. Based on its size, its distance from the Sun at roughly 4 billion miles at closest approach, and the general models of how small icy bodies in the outer solar system behave, the scientific expectation was that Pluto would resemble large moons like Callisto in the Jupiter system or Oberon in the Uranus system. These are bodies that are geologically dead, their interiors long since frozen solid, their surfaces heavily cratered from billions of years of impact history, their terrain essentially unchanged since the early solar system. There was no obvious heat source that should have kept Pluto geologically active. There was no large nearby planet exerting significant tidal forces on its interior. There was no reason, based on the available information and the prevailing models, to expect anything other than a frozen, cratered, ancient surface. This is why the New Horizons imagery was so genuinely shocking to the scientists who had spent years working on the mission and who had formed their professional intuitions about what they would find. The smooth plains, the convecting nitrogen ice, the mountain ranges, the cryovolcanoes, the atmospheric haze. None of it appeared in the predictions. The mission team had worked for nearly a decade preparing to study a world they had mentally modeled in a specific way, and in the span of a few hours during the closest approach, that mental model was comprehensively dismantled.